Okay, hi everybody, welcome back from the lunch break. I'm going to be chairing this session. The first talk is given by Bligaard from DTU, who's telling us about the B-class exchange operation.
Thank you. Yeah, so I work on catalytic science in general, and what we're trying to do is to integrate theory with synthesis, experimental characterization, and testing of catalysts to come up with novel catalysts for given catalytic reactions. And what we see more and more in the past decade or so, machine learning and data science is sort of being used to analyze various of these aspects of catalytic science more and more, and to integrate them. What I'll be talking about today is specifically sort of trying to come up with some machine learning inspired approaches to study the theory of catalytic science. What we really want to do is to carry out this design of novel catalysts where we start with some functionality, for example, the hydrogen evolution catalyst on the electrode, and then say, based on atomic scale simulations, can we come up with sort of a novel material? This inverse design problem is difficult to solve, and for many cases of this, it would be very nice to sort of not just be able to, if we start with a density functional theory foundation of some material and try to derive its properties, come up with not just a property, but an uncertainty on that property, given that there's some uncertainties in the electronic structure calculation still. And so what we try to do is to come up with some exchange correlation functionals that perform well for catalytic systems so that we can do modeling on these, and then at the same time give us uncertainty estimates based on the uncertainty so that we can underline the electronic structure. So in order to do this, we need sort of typically a data set or some data sets of properties that are reliable to begin with. We have our model space of some shade of exchange correlation functionals with some free parameters that we're trying to optimize, and then we perform some model selection within this model space based on the data sets to try and come up with a null functional. So we've looked at lots of different materials properties that can be interesting for catalytic science. And maybe the first one here is the least interesting. So molecular optimization images, something very often used in fitting functionals, but quite irrelevant for catalytic science. Well, it's good for historic reasons anyway. But we also have sort of very carefully experimental resorption images measured with the microcalorimetry on precision metal surfaces, gas phase reaction barriers, which could be important in some catalytic cases, and I think online they can see the, can they see the presentation? Just a second, we'll try and see.
Well, according, yeah. Okay.
Well, maybe some of the others. Okay, so gas phase reaction barriers, gas phase reaction images, very important in order to get equilibrium constants, for example, correct, of the overall reaction that we're looking at. Some things that would also be nice, typically the solid state cohesive images related to the stability of the catalytic material that we're looking at. Solid lattice constants, with wrong lattice constants, one gets wrong absorption images, so this can have a significant influence. And then more and more, we're looking at things containing sort of weakly bonded systems where non-covalent bonding to the surface can be important. So we've included this Pyramid S22 database. And so we have sort of some small databases, not many materials. These numbers down here signify sort of the number of systems that we have in each one of them. In this one here, there's some 100 optimization images. But often it's very important to have high quality data when we're doing this fitting rather than having much data, but with some of it more questionable quality. So a lot of sort of effort goes into sort of finding something that we trust in when we're doing these fits. And then we're basically here fitting an exchange correlation functional in a GTA formalism, so where we have this reduced density gradient and calculate an exchange energy density. That's the exchange energy density of the uniform electron gas multiplied by some factor, which is a function now only of the reduced density gradient here. This is integrated over all of space. And that looks a lot non-linear to begin with, so that could be quite nasty. So the approach we've taken is to try and sort of linearize everything from the outset. And this approach was developed by Søren Frederiksen and Jim Sedna and Carsten Jacobsen back around 20 years ago to a large extent. And what we've developed now is functionals that can actually be used and are competitive in accuracy for many of the catalytic systems that we're looking at today. So in order to do that, then we need to sort of be very careful with the basis of functions that we expand this exchange enhancement factor in, which is a function on S which goes from 0 to infinity. So we map that interval from 0 to infinity, we map that down to an interval between -1 and 1. And it's just done such that sort of the mapping is such that it focuses a lot of the new space between -1 and 1 is related to sort of the part of the interval here between 0 and infinity in S, which was sort of close to 0, which is the one that's most important for determining sort of typical systems exchange energies. Then we just expand the exchange enhancement factor in such a linear expansion where these functions V here are just orthogonal polynomials in this interval between -1 and 1. So now everything is linear, and because these are orthogonal in this interval, then everything is well behaved. And we would get sort of the total exchange energy would then look something like this. To figure out exactly what function this is of S, but one takes the function G of S in here before one takes the polynomial B, right? And so we have an exchange energy expansion here that in principle we could expand in now infinitely many functions. The first 7 functions look like this. So there's a constant here, that's function number 0, and then with more and more oscillations in this interval, but sort of the transformation from S to T sort of focus things in here and very little out here from 5 to infinity. So using that expansion, well, we also put in some non-local correlation because of these sort of covalent bonding systems we're interested in looking at. And then some normal correlation here, some LDA, some factor times LDA, such that LDA plus PV adds up to 1 in this coefficient. But that's sort of a small technical detail. Basically, it's just a linear expansion of the exchange correlation energy now in terms that can be calculated individually. And then something that sort of really took us a long time to get okay, so that we actually gave functionals that were useful, was to come up with criteria that when we regularize the fitting of these functionals, that we get something that hasn't gone too haywire and doesn't tend to overfit. And we've figured out especially that we can look at the second derivative of the exchange enhancement factor. If you look at the size of that squared, so something that, so looking at an integral of the squared curvature of this over the space from 0 to infinity, or here we've then substituted the t from -1 to 1, right? Then that gives a measure which sort of makes sure that sort of the different oscillatory functions we have, that we don't get too much of something that's very oscillatory and end up with an exchange enhancement factor that, because of the very little amount of data we have gives us two oscillatory exchange between these vectors. So with that, everything is sort of set up so that it's nice and linear. And basically what we get is linear sort of ordinary least squares fit. So this here is basically an ordinary least squares fit. Like you normally get an ordinary least squares fit on a quadratic cost function like this. We now have a penalty here, some regularization factor omega times, this is called the Tibanov matrix, which is just a metric on sort of how much our parameters, our linear expansion coefficient varies from the parameters set to some reasonable function like PD. And with the way that it's written up, one can calculate explicitly the elements in this Tibanov matrix based on these polynomials. And if they're chosen in a smart way, then this behaves very well and is invertible. And one can transform the problem to basically look sort of like a normal regularized small penrose form. So with that, this highly nonlinear problem of coming up with normal exchange relation functionals has turned into a linear fitting problem. And the only thing that we really need to do now is to figure out what. Well, so yeah, L here I should say L squared is practically an identity matrix. It has a couple of zeros in the diagonal corresponding to those functions that where the second derivative is 0. Our main problem is now finding this regularization parameter. And for that, we just use simple one flavor of cross validation. And here, this is written as the effective number of parameters. That's just sort of where omega is, how many eigenvalues it was chopped off in the singular value decomposition of X. So we just take the minimum that we find in such a plot here, and one can just do one singular value decomposition and then calculate all of these. So it's really very cheap to perform this optimization where you've done all the DRT calculations that's in the data sets from now. And as one can see here, one has only sort of very few effective parameters in fits like this. There's actually not that big necessity to sort of have a lot of variation in the exchange relation function. Sort of 7-8 degrees of freedom is adequate. Now, one problem is that when we make a fit to the different databases here, consumption energies, reaction energies, you sort of get very different exchange enhancement factors. Now, you see all of these are nice and smooth because we penalize this integrated second derivative squared. So they're all nice and smooth and well behaved, but they're quite different depending on what data set they're fitted to, meaning that basically you can fit to this data set of absorption energies or this set of reaction energies, but you get very different functionals, and trying to fit to both of them is now sort of a problem. One could, of course, just make a database where all the systems from one and all the systems from another is in. Then you sort of lose control of how important those reaction energies compared to absorption energies. It also is annoying in the sense that if you add more system in one database, then sort of the weight of that database ends up becoming more important for the fit that you end up with. And we'd like these fits to be sort of stable over time as we try to extend these databases. But you see very different sort of, here, this is the amount of correlation, LDA correlation we have in the functional varies a lot between 0 and 1. The number of effective parameters vary. So the LDA limit should be 1, right? You can set it free here, and you can sort of vary up to 14%. This sort of way it comes where it should go to the Bligaard for perhaps, but they end up in quite different places. Now, if you fit to a certain database, and then here you fit to each of these databases down here, and then we see how well does it perform on each of the databases compared to how well it could perform. So in the diagonal here, we would have ones, and then if you fit to chemisorption images, your reaction images turn out to be about 3 times worse than what they could have been if you had fitted to your reaction images. So it's often nice to look at plots like this. You can see everything is sort of quite uncorrelated, except if you fit to the S22 database at 0.9 times the van der Waals distance, it's very correlated to what we get at 1.0 times the van der Waals distance. So those two databases are quite correlated. Everything else is sort of quite uncorrelated. So really, depending on what data you're fitting to, you would end up in very different functions. So the way that we have sort of found around this, that is, I think, a practical way of looking at it is if you look at two databases. So this is the relative cost compared to how well it could be. So one corresponds to you fitted to this database here, the G2 database with 97 atoms. Then how well do you perform on this other property, the van der Waals data? Then it's 40 times worse or something than what. Or if you do the optimal fit down here to this data, you'll end up sort of way up here, 5 times, 4 times worse in this database. So what we see is this factor 40 here is very different from this factor down here. So there's some things. So this curve is universal in the sense that there's always sort of a hyperbolic curve here that goes from 1 in this limit to 1 in that limit. But exactly how that curve goes is quite sort of depending on what two materials properties you look at. So how do you weigh sort of where you want to be on this? It's really sort of a question of how much weight should you put on one database compared to another. And the practical way of looking at this Pareto optimality problem, right, where you want to do both well, but you can't do both well at the same time. So you put some weight on each one of them. Sort of a natural point to be at is the point where if you make one of these data sets that fit to them 1% worse, you'll make the other one 1% better. Or if you think that one of them is much more important than the other, you could put on a different weight, higher weight, so that if you made 1% better, you would make the other one 2% worse. You put on a weight 2. And the way to do that mathematically, sort of in a way that's very easy to implement, is to basically make a new cost function, which is just the product of the original cost functions. And the weights that I just talked about, they are sort of the exponents in this product. Then you want to minimize this, which is the same as minimizing the logarithm of this. And you end up with a criterion like this. And basically, sort of the usual way of optimizing your cost function, which would sort of be something like this, right? But with new weights that are these WI or CI. So he turns this sort of highly speculative problem into, again, basically just a linear fit, but which we now have to do iteratively because these CIs change. So with that, we can now fit to all the databases at the same time with some well-chosen weights and get one common functional, that's this BW functional here. And you can see how it's pretty close to sort of being between PBE in some sense and RPBE or RPBE. And it goes up a little bit steeper and it breaks the LGA limit here because we did it a little bit. And then, of course, it has on top of this some non-local correlation. And so this functional ends up being sort of not the best at anything. Well, actually, maybe it's the best at this database here, the G3, that didn't matter, right? But it's sort of not significantly worse than the other functional we would use for catalysis science, the RPBE here, at any of these properties. But for van der Waals systems and things like that, it's significantly better. So in that aspect, it's sort of an improvement on the functional that we have otherwise been using for the past many years. And we can see here, if you sort of look at this sort of a typical plot of the surface energy here of platinum 111 and the CO absorption energy on platinum 111. the GDA functional fly out here, and if you add van der Waals contribution, the BBW2, you can sort of move that line up here. The real result is expected to sort of be out here, the experimental or the RPA result. And BBW should then lie on this line here, the red line, and it sort of does. Maybe breaks this a little bit because we let it wiggle a little bit more. That's a functional wiggling. But this is sort of very typical behavior that you can get. You can sort of try to get something that's sort of as close as possible to several properties you want to model at the same time. This for something similar. So this has been used in many cases now, for example, you can check out this absorption of CO in an X-ray laser. Now the modeling is going well, meaning that you can actually see things sitting on the surface, whereas in a zeolite, for example, if you have alkane absorption in a zeolite as a function of the length of the alkane, it's known experimentally that you should find stronger and stronger. And the B functional or BBW functional will bind stronger and stronger, whereas the functional we have used before would have sort of a qualitative error in that kind of model. There are other systems where things go well. Now, sort of, this was sort of one aspect. It's not too bad a functional. It's not great at anything, but it's not too bad. But more interestingly, it implements this what I call the Sedna-Jacobson ensemble. So that is basically that it sort of now gives a probability distribution of the parameters in the functional, which according to the Sedna-Jacobson sort of expansion, you would expect to be e to the minus the cost function as a function of these parameters divided by some temperature, where the temperature is 2 times the cost function of the best fit divided by the number of effective degrees of freedom in the fit. And if you choose that, that's just a choice, right? And it's a different choice from a Bayesian posterior distribution of the parameters. But with this choice, you get that the standard deviation that you calculate by calculating a standard deviation over this ensemble is reproducing the standard deviation on the fitted data that you fitted to originally. So if you're using a Bayesian posterior distribution for your coefficients that you're fitting, then you will find that as you add more and more data, your parameters get more and more well determined, and eventually you sort of get delta functions, right? They're extremely well determined, and they say, oh, the parameter is this. It may be sort of still not a good model because your model space is not big enough to actually include sort of the real quantum mechanics in this case of what's going on, right? We're in this GTA model space, which is far from being a complete representation of the quantum mechanics, right? And so the posterior distribution would not give you an uncertainty on the parameters that you can use to sort of predict uncertainty on new problems. It'll sort of give you the uncertainty of what model should you choose within that space. But then there's sort of the additional problem of sort of all the deviation from the model space you can fit into the actual model space that exists. But the Sedna-Jacobson ensemble has that great property that it really reproduces the errors if it's done in this way. And so there's a lot of technicalities in how to do that with multiple databases and things like this. I'll not get into, but you can sort of see here that we do get that properties, there's definitely not a perfect correspondence between sort of what we observed with the BVW and the ensemble estimate in this case. That is because we had to sort of do multiple databases at the same time, right? But these are chosen so that they're an average pretty good. And those quantities where there's sort of intermediate errors, your ensemble predicts intermediate errors, those where there are big errors, the cohesion integers here, there are also big errors in predicted ensemble. Those where there are very small errors like the very small energetics of sort of long distance and around one. They're also predicted to be small, but out here, where this is sort of a big discrepancy between the model you're using, the model space that you're trying to optimize in, and sort of what is really going on, maybe those errors can be wrong by some factor here, a factor of 3 or 4. But we found in a number of cases this is pretty useful for error estimation. And for example, we can plug this into a microkinetic model for the turnover frequencies, in this case, ammonia synthesis. So make some typical mean field microkinetic model with no interactions and steps of a catalytic material, and then here plot what is predicted from the model compared to the experiments. And this we would typically say is a good correspondence. This is the logarithm x10 of the turnover frequency. So we all find order of magnitude. So the question is whether we can say that's good, right? And here we have the transition state energy model compared to the apparent effective barrier of the problem. And this is also a pretty good correspondence. We would normally say the question is sort of how does one sort of really quantify this, right? Now with the ensemble, let's say you take just 2,000 functionals, which you can do easily, but you can evaluate them non-self-consistently, so it doesn't have more really than the normal. Then we can sort of see where these ensembles are, and they definitely sort of are all over the place here, right? We can also model one standard deviation, and now we see that these results, sort of 2 orders of magnitude in turnover frequency, is within the standard deviation and the exchange correlation function. And over here we can see that the experimental measurement is also within sort of a prediction. 2? Oh, yeah. Well, I mean, I think I made my point. Let's just stop here. If you have any questions, then you can take some time for questions.
In the last plot that exactly this plot that you show, is it just a case for different functions, but not the uncertainty that production of the functionals contained by each?
In this plot here?
No, the next.
Oh,
yeah,
this one?
that.
So
the various shades that you have in your plot is the effect of different functionals trials, but not the uncertainty that each result of each different functional contains, right?
Yeah, it's it is the one standard deviation of this ensemble of functionals around the optimal functional, which is the best fit functional in the model.
Is there something you want this for the interpretation of
Yeah.
How that counts for mobile?
Yeah, it's basically because it was made by physicists, so they want everything to look like a temperature. But basically, it's just the factor you want to put in here. You want to have this to be, let's say, per degree of freedom, right? You want this to be minus the cost function over 2 times the best cost function in order to get sort of this standard deviation that you have over here. And since the things that are here are really basically the things that go into the, I mean, it's really this is really the first term of the cost function. And then there's the regularization to the right. So it's only correct. They didn't regularize this when they derived it back in actually, in this paper here. So in that case, it's exact. Because we regularized it, there's sort of slight variations from this, but it's sort of just to troubleshoot making order to sort of have a standard option.
I'm wondering if this change of coordinates from S to T, where you really put a lot of emphasis on the relevant part of the enhancement factor. How important is that really for the overall error spread, for example? Because I would imagine if you sort of are too floppy in parts of the model space, which is not so relevant for the chemistry, this will sort of screw up and misdirect also your errors.
So the original functional from 2005 by Mortensen and Sedna and Fasniarty, so the first Bayesian area estimation functional, that has some of the properties you sort of want in a functional. But what they fitted there was, instead of making this transformation from S to T, they just took sort of powers of S, basically, almost. And they get very highly linearly correlated when you get to higher powers. And so you get a very ill-conditioned problem. And even sort of trying to treat this sort of as a sloppy model makes the sort of the derivation of which functional should then have sort of two oscillatory, right? So I think sort of it's key to make it well posed and not get a too ill condition to sort of try to do something like this. Sort of in the relevant part of your S space, which shows you trying to focus in to get something that some basis functions that are really not too linearly. And then the second thing is really penalize sort of things that you find unphysical. And so in Weymuth style, you have a functional that sort of really goes from LPA to Oxford bound very smoothly. And that's a very good idea. And you don't need many oscillations on that exclusively before you can find things that will go really wrong. I mean, you can also come up with artificial things that you know would go terribly wrong if you have sort of too many oscillations in that function. So you really want to sort of not mess that up too much. So you want something very smooth. On the other hand, you do want a little bit more flexibility than sort of just picking PD or something like that. So you do need to represent some variation there that would be flexible more. So you want, I think most importantly, you want something smooth. And actually, Kieran Berg, when he was working on the PDE functional, trying lots and lots of different functional forms, trying to get the LDA bound and the Oxford bound, right? And then what they actually have in the PDE functional is sort of the one that sort of matches the things that are best possible, right? So in a way, that's a little bit similar, just choosing an expansion and then trying to find the best expansion, but under the constraint that things are very, very smooth. So I think it's sort of still in the sort of Weymuth style approach to sort of really try to kill any oscillations. And this also makes it much more focused.
Okay, thank you. I think we should probably move on. Let's thank Thomas again. Sticking with the theme of so the next talk is given by Kate Fisher from
Thank you. Good afternoon. I'm going to be speaking today about our plans for a Bayesian inference approach to uncertainty quantification for density functional theory predictions. This is a project I've been working on with Michael, as well as Lisa, starting this up. At this point in the workshop, we've seen several examples of cases where DFT predictions are useful as references in higher scale simulations, particularly molecular dynamics simulations. And we're all aware of the danger that can occur if we're using these predictions as reference values without taking into account how different approximation choices can affect the actual DFT predictions. In this work, our plan is to take an ensemble of predictions using different approximation choices and infer a probability distribution on some quantity of interest. This will help us make improved predictions, and the aim is to be able to get some uncertainty information from the variance of probability distribution. We're going to be focusing on the effect of the choice of the exchange correlation functional approximation. This has been mentioned in previous talks as a major source of uncertainty in DFT. Many different approximations exist to the exchange correlation functional, generally categorized by the Jacobs ladder framework, where higher ones are associated with approximation types that include more quantities and are more computationally simple. We want that to mean that they're more accurate, but in practice, given an ensemble of predictions, it's difficult to make assumptions about their relative accuracy. So this is information that we would like to kind of explain. We have a few long-term applications in mind for this type of work. Yesterday, Dallas mentioned the MIT assessments project, where we're aiming to have multi-scale modeling of materials in extreme environments, such as high-speed flows or extreme temperature. And this work would be part of the bridge from DFT up to molecular dynamics as the uncertainty computation component. Some other potential applications would be to guide the design of new functional approximations, or to guide multi-fidelity approximation in cases where there's a budget for the use of a few functionals, and we need information about which functional approximations should be used. There has been some work previously towards uncertainty quantification for density functional theory. I'll summarize only a few examples, but one approach would be to use regression to relate DFT predictions to experimental data. In this case, I'm summarizing a method that uses linear regression to fit the predictions to the experimental data, and fix them with weighted least squares, so in principle other choices. And the main idea is to separate predictable error from error that could be modeled with a random variable. We've just seen an explanation of another influential method for uncertainty quantification in DFT. That's the Bayesian error estimation functionals, or BEAT. I'll be quick, but essentially an optimal functional approximation is found, and ensemble of other functional approximations are generated, such that the spread of the ensemble is representative of how far the fit is in the databases used. In our setting, we are going to start by taking some system that we call Y, and some quantity of interest. In this case, we're working with atomization energy. And we assume, well, we can say that there is a true value for whatever quantity of interest we're looking at. We'll call this Q. Our assumption comes in where we say that experimental measurements and various theoretical predictions, including DFT, are distributed around this true value in some way such that we can choose a statistical model that describes the relationship between these predictions and the true value. By picking a statistical model and a set of parameters that relate you to the data, we can set up a Bayesian inference problem where we'll infer a probability distribution. This approach is adapted from a method that's used for uncertainty quantification in climate science. This is because the climate scientists face kind of a similar problem in that they have many predictive models available to them. And it's not clear what hierarchy the models should be put in with regards to their relative practice. In the realm of climate science, the method involves constructing an ensemble of different predictive models. You take the predictions these models make for the current temperature and compare them to data for current temperature, as well as taking predictions of the models for the future temperature, for which there is no data to make them easy validation for their predictions. All of this data together is used in an inference problem in order to get probability distributions on both current and future temperature. When we move to the DFT setting, our initial approach to translating this method is going to involve picking two chemical systems. Our chemical compound X will be analog to current temperature, and that will have some reference data that we can compare DFT predictions to for X to. We will also have a chemical compound Y that we will say is analogous to future temperature, because we do not have the reference data available to the model. But we will take the set of ensemble predictions for Y as well as X and the reference data for X and use these as data in our inference. Please excuse me.
Oh, sorry.
Yes.
Seems there is a problem with outlook.
Yeah, I don't think there's much we can do at the moment.
Is it that I'm too quiet, or is it just that?
Yeah, I've tried to speak up a little if you can. I don't think there's much we can do.
There's a range of different results we can get by applying this inference model. I'll give you an example of just two before getting more into the assumptions that lead to this case. On the left, we have the inference results for the X system, which again is the system where we have reference data available to the model, marked by the black dashed line. On the right is the results for the Y system. We have reference data marked here, though that's not available to the inference model. Individual DFT predictions are shown as X's across the x-axis. In the top case, the model is apparently performing well by a qualitative check because it seems to be relatively representative of both the reference and DFT predictions nearby to the reference. So in the bottom case, we can see that there can be limitations to this model. The posterior distributions that we see are narrow, and in the Y case, not aware of where the reference is. In the coming slides, I'll talk more about the assumptions that we've put into place in our preliminary implementation of this model, and how they might be adjusted. In order to obtain the probability distributions from our data and assumptions, we make use of Bayes' law, where essentially we choose a set of parameters that we relate to our data, and describe these by our choice of likelihood prior distributions, and obtain a posterior distribution on that parameter set informed by our data. In this case, we have three types of data going into the model, and I'll briefly describe the notation. System X, again, is the system that we have reference data available for, called X naught. We index our functionals in our ensemble by J. where our predictions for X are xj and the system Y are yj. There are also many choices we can make about the statistical models that we're use to represent our data. And we're starting with a relatively simple case in order to understand how the model works in the setting with two different systems before we will expand it in future cases. The important aspect to note about our choices of likelihood is that if we look at our reference data for X, as well as each DFT prediction that we make for X, these are all drawn from distributions centered around a common value mu. In this case, we consider this what the model believes to be the true value that the data points are distributed around. We define a conditional distribution for yj, but if we are to direct the marginal distribution, we find a similar case to X, in that all predictions have a common mean value mu, which could be conceptualized as the model's idea of the true value for our constitutive interest for y. We allow yj to be conditioned on xj with correlation control by parameters beta and e. We also define precision parameters, lambda j for each functional, where they represent our confidence in that particular functional, such that lambda j is the inverse of the variance of xj, and up to the constant, the inverse of the variance of yj given xj. So that if our precision value is large, the variances are small, and we're more confident in the prediction. We choose uninformative patterns to start out with so that our data will largely inform our inference. And our important fixed value here is lambda not inverse, which controls the variance that we set for the reference data for X. This figure is meant to help visualize how the model chooses distributions for different data points. It's a bit of a simplification because the aim of the model is to get distributions for both mu and mu, which are here for simplicity treated as point values. But the aim is to show the different distributions out there. If we start at the top part of the figure, we can see the different types of data available for X. The DFT predictions are X1 and X2 here, with reference value X naught shown by a dot. The model has some idea of the variance of the reference value with respect to mu, and can see how the position of the data points relate to each other. And it uses this information to infer distributions on, or to infer the parameters for the distributions on each of these data points. There are also, for X, all of these distributions are centered around a common mean that have different variances related to what the model infers the quality of the functional predictions. When we move to Y, each of the data points from DFT are still available to us, but we no longer have a reference value available to us. As in the X case, each of the predictions are centered, each of the predicted distributions are centered around a common value, in this case mu, and has a different variance for the distribution. These are not the same as the variance in the X case, but they're related by a constant. So if the variance for x1 is broader than the variance for x2, the variance for y1 will be broader than the variance for y2. Even before we get to the results of this particular model, we can say a few words about its limitations to be aware of how it will behave and how we may modify it. A particularly strong assumption is that each of the predictions and reference values share a common mean, which means that we're assuming that the DFT functionals have no bias, which we know is not the case in practice. Additionally, when we set our likelihood functions for our different distributions, we've made the assumption that predictions by different functionals for the same numerical system are independent of each other, which is a strong assumption given that many functional approximations are similar in construction. We've also started by using informative priors, which seems to work well in practice, but this is an area we can look at further. Finally, since we're looking at only two chemical systems, we have somewhat limited information when estimating our precision parameters, as it's a bit of a simplification or large assumption to assume that the functionals that perform best for x will always perform best for y. On a practical note, in order to perform inference, we have a relatively small parameter set. So we're able to use MCMC fairly efficiently with good sampling that takes advantage of our conjugate priors. We've done some diagnostic checks to see that we seem to be actually sampling from our true posterior distribution. For example, shown here are some trace plots showing the MCMC samples obtained for one of our friends. We can finally return to one of the results that I've shown earlier in this talk. This results from comparing two relatively small chemical systems that are chemically related to each other. As a reminder, the black dashed lines are the reference values for the system, and the reference value for y is not available to the inference model. The individual DFT predictions are given by the x's across the dashed lines, and the dotted line in the x space is obtained as a weighted mean of the DFT points against using their distance from the reference as weights. It's interesting in this case to see that the peak of the posterior distribution for x is not exactly on the reference value, given that this value is known to the model. And this is because we allow some variance for the reference. So it is swayed by the fact that relatively close to the reference, there's a cluster of DFT predictions that are close to each other, and that's where the peak of the posterior is located. Similarly, in the y case, we can observe when we check which particular functional predictions are which, that the functional predictions where the posterior distribution is non-zero for y are the same as the functional distributions where it's non-zero for x. We can also observe that the peak of y is located where there's a cluster of relatively highly weighted functionals close to each other. That happens to be close to where the reference value is, so we end up with a good result from this distribution. We also have a relatively high non-zero value over a functional prediction close to 430 kilocalories per mole. So using this functional prediction, which is kind of off on its own, has such a high value of the posterior above it is because it's the prediction that performed best in the X case, and it was given the highest rate. We can compare different types of chemical systems, in this case, two radical compounds, and see some similar good results in that the model is able to determine where the posterior distribution should be close to the edge of the DFT ensemble, as long as X and Y are a good match for each other. This particular case can at first glance seem to be the result, in that both posterior distributions are very close to the reference value. However, they're very close to the reference value and kind of worryingly narrow. The distributions are only have significant non-zero values over one of the prediction. Okay, thank you. If we take the same X prediction and use a different Y prediction, we can see that the previous case where we were directly on the reference was a coincidence. And what occurs is that when there are certain circumstances when the model can overweight one particular DFT functional and make a inference that is not where the uncertainty is not meaningful. And these are limitations that we will have to address with our predictions for this model. Another example of a case we come across is where we see something that if we did not know the reference value for Y, we would think we had a fairly good result because our posterior distribution for Y shown on the right is relatively representative of our ensemble. It has a wide distribution, but it's just not close to where the reference value happens to be and have no information in order to reach this reference. We can get insight that the functionals for these two different models behave very differently, and draw the conclusion that these two chemical compounds shouldn't have been put together in comparison. This is a major starting point for revising our method in order to make sure that we're providing useful information for the reference for the chemical system we're trying to learn, and more varied information in the form of multiple systems. This is a brief overview that just gives an idea of the scale of the error we're seeing. And I'll give a few words on the next steps. The major point is when I alluded to through our results that when we're comparing only two systems, we're limited in the information we have to make an inference. So we're looking at developing a case where multiple systems would be used to make inference. We're also working on revising the model to incorporate biases and revising our process to incorporate ways to check the model when no reference value for Y is available. Thank you for your attention. Please excuse any talking, and I can answer any questions.
Thanks, Ed. Questions? Cass.
You were sampling some Monte Carlo, right, for this new system. What was the size of your models, roughly speaking? Like how many parameters were you actually sampling? Just in general.
It's dependent on the number of DFT predictions that we use. However, if we're only using 10 DFT predictions, that ends up being 10 precision parameters plus 2 mean parameters plus 2 correlation parameters. So not very little.
No, it's quite expensive, right? But for 14 or something, we just mentioned. Certainly.
Yeah. For this combination of likelihood and prior, we're able to use analytical updates to most of the parameters. So it takes on the order of seconds.
Yeah. Thank you.
While you're on that slide, can I just ask a related question? I noticed you're fixing the A and B parameters that describe the model descriptions, subject to simplification. Or would you ideally include them as running variables as well?
These two variables are the hyperparameters for the gamma distribution.
Okay, the difference
Yeah.
the A and B that you mentioned.
Yeah, I'm sorry for the
No,
confusion.
that's fine. Any other questions? Thanks.
Yeah, maybe this is more a question for the room, but symmetrically is something that depends the correlation between these different functions. And I realize that there's no hierarchy, but is there a way to estimate a priori some expected correlations between behaviors of these functions?
If there was, that would be something we'd be very interested in. So we're open to any ideas.
Maybe you can show the slide with these 4 or 5 systems. C2 and CH. Know which one? So what we're doing here is we're doing like similar-ish systems, and we're just showing the ordering of the functionals, and it's not really visible on the spot. There's some, like for nice systems, they're somewhat correlated, but as soon as you get something that you teaches doesn't do good, like C2, where you have strong correlation, then the order is not. So, sort of exactly for the cases where you want some model like this to work, it's hard to say. So, but that's at least the conclusion we had on the data.
Questions, comments? If not, let's thank Kate again.
Are the people online hearing me well? How is the sound? Anyone back?
It's like just disconnected.
Yeah. How is it now?
If I understand it right, now you are fully on this microphone, not on the room system.
Both.
Okay.
System also.
And they kind of overlap?
Yeah. Already
Let's hope for the best.
If it would be heard. So
Okay.
yes.
Good, let's take that as a go, because we are in Switzerland, and that means we have to adhere to Swiss precision and start exactly on time and finish exactly on time. So we have 3 speakers for a half an hour in this afternoon session, and Genevieve Dusson is the first one. Please.
Thank you very much. So, sorry, I forgot the pointer. So
Yeah, that's the point.
This one?
Exactly. Yes.
yeah, okay. Good. Is that? Yeah, perfect. Thank you. Sorry about this. In this talk, I'll be more on the numerical analysis side of the workshop, and I will present some work on how to get guaranteed and computable bounds for eigenvalue problems. So this is a joint work with Eric Ansès, Yvon Maté, Benjamin Stam, and Martin Boalik. And so the motivation, let's say, for looking at eigenvalue problems is problems like what appears in DFT. So, for example, in the culture model, where you want to compute the electron density of a given molecular system. And so, mathematically speaking, the problem is PDEs with m nonlinear eigenvalue equations in 3D, where m is the number of electrons in the system, and where the operator that has to be diagonalized is minus Laplace plus some potential, which itself depends on the electron density of the system and the positions of the atoms. And so there are a few difficulties to estimate the error for such problems. So first, there are several eigenvalues that need to be computed. These eigenvalues can be possibly degenerate, and of course there is the nonlinearity in the operator. So the main question I will focus on today is how to estimate the discretization error for such problems. So the discretization error is basically the error that you make because you're using a finite basis set to solve the problem in practice. Okay, so let me first try to sketch out kind of a wish list for what a good error bound would be. So basically we have the computed solution that we get out of the computer code that we use to solve the problem, and somewhere we have the exact solution. And so the goal of this work is to derive an inequality. So the goal is to bound the error between the exact and the approximate solution of the problem, but by some terms that depend on the different approximation parameters of the problem, such as the discretization, the algorithm, etc. And so there are a few things that we would like to be satisfied by our error bound. And so first, of course, it should be an upper bound of the error that is computable, so that we can actually compute it. And then it should be valid under checkable assumptions. What I mean by this is that we want to be able to say whether our computations is fully guaranteed, and if not for any value of the parameters, at least asymptotically, but in an asymptotic way that we can control. So we want to be able to say, okay, from this parameter on, then the bounds are guaranteed. Then we want this bound to be efficient. So this means that the upper bound of the error should be close to the exact error, otherwise the bound is useless. Because, for example, if you have a bound that is something like 100 or 1,000 times higher than the actual error, then you don't have really meaningful information from this bound. And the last thing that we also would like to have is a bound that allows for adaptivity, which means that we want to be able to separate the error between the different approximations that are made to compute the solution, in order to be able to refine only the parameters that are needed to reach an optimal accuracy within some given computational cost. Okay, so the outline of my talk will be as follows. So I will first focus on an error estimation for a linear eigenvalue problem, so freezing potential. Then I will talk a little bit about what we can do for a nonlinear eigenvalue problem, and at the end I'll talk about error balancing and how we can do in practice to balance different sources of errors. Okay, so our goal here is really to add error bars to the eigenvalues and eigenvectors of the simulation. So in such guaranteed bounds for eigenvalues problems are not really new. So they, because eigenvalue problems appear in a lot of different contexts, including vibration problems in mechanics, neutronics, and so error bounds involving the eigenvalue estimation were already sought for already in the 50s, for example, by Cato and Argand and these kind of things. And so I would say that the error estimation for both the eigenvalue and the eigenvector is a bit more recent, but in all of the works that were existing at the time we started this project, there were always some limitations about, for example, some uncomputable terms or some restriction on the method that was used. And so that's why we decided to try and do these error estimations ourselves. Okay, so just to give a little bit of the setting on the mathematical setting of our problem. So I will consider a given operator that I call A, which is basically in the context of chemistry minus Laplace plus our potential, which is self-adjoint, bounded below. So for simplicity, I will just shift the operator so that it becomes positive. And also it needs to have compact resolvent for the bounds to be valid. So in practice, this means that there exists a sequence of eigenvalues going to infinity and corresponding eigenvectors satisfying the eigenvalue problem. Then we discretize the problem, so we find approximations for the eigenvalue and eigenvectors of the problem, and we want to find guaranteed error bounds for the quantities. So basically, the error in the eigenvectors and the error in the eigenvalues. Okay, and so our approach is the following. So it will be based on the residual of the problem. So the residual, which is defined here, is basically the error of the approximate solution with respect to the equation of the problem. So, for example, if you replace here these the eigenvector and the eigenvalue by the exact ones, then the residual is 0. So, in a way, it's a kind of good indicator how well you solve the equation. But then the whole game is to manage to link the error on the solution to the error in the residual, because the residual only depends on the approximate solution. So in a way, this is something that you can compute, whereas the error between the exact and the approximate solution you cannot compute. So the way we did it was first to link the quantities of the different errors, so between the eigenvectors, the errors on the eigenvectors and the eigenvalues, to some norm of the residual. So this is here the dual norm of the residual, which involves basically inverting the operator A. So in practice, this is not easy to compute because it requires to solve a problem on the continuous space. So in practice, this is not feasible. So there are ways to estimate this dual norm of the residual. So here there are kind of two different ways to do it, depending on the discretization method that you use. So for finite elements, there's, let's say, one way, and for if you use plain waves, so Fourier discretization, then what happens usually is that it's possible to estimate this norm by the H1 norm of the residual, which in Fourier can be exactly computed. And so then the third step is to estimate a few constants that appear in those abstract estimations. And these involve lower and upper bounds in the eigenvalues. And so I will show how we can kind of estimate those in order to have bounds for the whole thing. And yeah, and at the end we just gather everything together. So then this is kind of the way to do it for a single eigenvalue. Now, if you have clusters of eigenvalue, what matters is really the span of the eigenvectors and the corresponding eigenvalues. And so the way to treat this is to work directly with orthogonal projectors onto the span of these eigenvectors. And so we have this way an exact orthogonal projector and an approximate one, and then we estimate the error in a norm that is called the eventual norm. So it's kind of an analog to the energy norm for the eigenvector. And for the eigenvalues, we just estimate the sum of the error between the eigenvalues. Okay, so really the key assumptions that we need in the following is just this one. So that this is a gap assumption. So basically, we need a gap between the eigenvalue that we look for and the following one, in the sense that the approximate eigenvalue must be below the exact following one. So this is in something that needs to be, of course, guaranteed, and this is not easy, but this is something that is difficult to get rid of, I would say. Okay, so this is the kind of the error bounds that we managed to derive. So basically, the error in the eigenvectors can be bounded by some norm of the residual plus some additional term that can itself be bounded by the same dual norm of the residual. So basically, replacing the estimation here by this line here, we get an estimate in the eigenfunction that only depends on the dual norm of the residual times some constants that appear here. So this basically is easy to estimate, but then here we have some constant that involves the gap between the eigenvalue that is sought for and the surrounding ones. And so I'll just skip this, which is how to estimate the dual norm of the residual in the case of finite elements. In Fourier, it's just bounding this by the h1 norm of the residual, h minus 1 norm of the residual. And so to estimate basically this constant, which involves a gap, we need basically crude bounds on the surrounding eigenvalues. And so this is in a way difficult because this is exactly the problem we are trying to solve. So it's kind of going in circles, but what we can use here is that we don't need really precise bounds, we only need coarse bounds. And so for this, we can use anything that is in the literature to estimate those bounds in those eigenvalues in a coarse way. And in practice, I would say this is quite important. We can use as a lower bound for the surrounding eigenvalues, the one that we compute we're using the discretization. So in that case, we lose the kind of the fully guaranteed context, but it works really well to estimate the pre-constant. Okay, so at the end, we can just gather everything. So we have here the error on the eigenfunction, which is bounded by the norm of the residual times this constant here. So this is for finite elements. We estimate this with some computable thing, and then we estimate the constant by something computable. And at the end, what we have is just that the error in the eigenvalues and the eigenvectors can be estimated with something that is fully computable. And even in a nice case where we have some regularity, what happens is that this error estimate is asymptotically just this term, which is basically the dual norm of the residual. And so this is the errors match the bounds exactly asymptotically. So I'll show a little bit, I'll first talk a little bit about how to extend these to clusters. And so the idea is really to, instead of looking at eigenvectors, looking at the orthogonal projectors. And so we have kind of a corresponding table between the one eigenvalue case and the cluster case. And what happens is that we estimate the norm, some norm on the projectors by some norm on the residuals. And the residual depends only on the approximate orthogonal projectors. Okay. And an important practical thing is that we don't want to code anything that involves the orthogonal projectors in total, because there are too big objects. And so in practice, we want to work with the eigenfunctions themselves. And the good news is that this norm that we use to control the residual can be explicitly expressed as a sum of squares of duonorms of the individual residuals. So in practice, we can basically compute everything with what was done for the one eigenvalue case. Okay, and yeah, and then there are some theoretical results guaranteeing that the error in the projectors corresponds to the error in the eigenvector if you rotate them correctly. So rotating them doesn't change the span space, and so if you rotate them in an optimal way, then you get back the error in the projectors. Okay, so let me show you just a few results. So this is just a Laplace operator on a square, so it's really a toy ball, not really related to chemistry yet. But what we see here is that, for example, if we take the error in the eigenvalue, so this is the blue plot here, and its estimate in red here, we see that first the error bounds correctly the real error, and also asymptotically, so when we refine the mesh, so going to the left, the two plots start to match, so which means that our error bound is really good and actually optimal asymptotically. Okay, so we can do the same for an L-shaped domain, and maybe a little bit more related to chemistry. So this is a Schrödinger operator, but it's in 1D in the box. And so what we see is basically the same thing. So so this is in red the error on the eigenvalue, and in blue the error error estimate, which they match pretty well. Okay, so this was for a linear eigenvalue problem. Now, what can we do when we go to non-linear eigenvalue problems? And so for this, I'll go to a work that I'll present some work that I did with Ivan Made quite a while ago, but I thought this is kind of in the theme of the workshop. So we're looking at a toy non-linear eigenvalue problem. So this is an operator with minus Laplace plus some potential plus some really simple nonlinearity. And we are in 1D. Yeah, okay. And so we solved the problem in practice with using the plane wave discretization and some set consistent algorithm, as will be done in for molecules. And so the question here is how to find a guaranteed computable bound of the error in the eigenvector and the eigenvalue. And so the main idea is to do a Taylor expansion of the residual. So writing that the residual of the exact solution, which is 0, is about the residual in the approximate solution plus the differential applied to the error. And so if we invert this equation, then we get that the error can be approximated at first order by the inverse of the Jacobian of the residual applied to the residual. And you see that on the right here, you only have terms that depend on the approximate quantities. And so what we did, so this is here in this approximation, there are higher order terms that you need to bound. And so the way we did this was first to kind of obtain a first cost bound that looks like this. using a crude bound on the error on the Jacobian of the residual times the residual, and then once we know that we have a first bound, then we write this right-hand side as something that looks like the Laplace operator plus some several convergent terms. And so in the end, what happens is that we obtain a first bound on the error between the exact eigenvector and eigenvalues, and this is the first correspondence that we can really compute, and we can really guarantee that it is valid, and then we can get an asymptotic error bound, but which we control through the first bound. And so in the end, what we obtain is that the error is bounded by something that we can compute times the dual norm of the residual, and this thing in front can be taken as close as 1 as we wish. And so this is a guaranteed, and that is a really good bound, but the problem is that it's only guaranteed if the error is small enough. And so numerically what we see is that this second, so in red here we have the exact error, in green we have the second bound that is really precise, so this works quite well. And the first bound is this one, so it overshoots the error, but on the other hand, it allows to guarantee up from this point on that the second bound is guaranteed, so we have a good error bound at the end. Okay, and so just if I have 1 or 2 minutes, so I'll conclude on showing how we can combine different sources of errors. And so the idea is to practically use these error bounds to obtain as good accuracy as we can with a given computational cost. And so, for example, if the error comes from different sources, so that I named 1, 2, 3, that could be some algorithm, the discretization, even some model error, then an efficient scheme would be to try to balance those errors. Because if you have an error bound, and if you have one error that is really higher than the others, then it's really no need to invest some time on refining the other parameters of the simulation. You really need to refine only the parameters that lead to the largest errors. And so this has been done on a few examples. For example, combining the discretization and the self-consistent flip errors for the problem I just showed. We also did some kind of balancing between discretization and eigenvalue solver in a different work, and also Michael and Antoine and Eric have done some bounds depending on both on the discretization and the algorithmic error. And so the main idea is to decompose the residual between things that only depends mainly on one source. And so, for example, here we have 2 sources of errors, the dimension of the space and the number of iterations in the SCF algorithm. And so we write the full residual as the sum of residual that depends on the dimension and residual that depends on the number of iterations. And so then at the end, we decompose the error, and we compute each of these terms at each iterations to do some adaptive refinement. And so this is what we get at the end. So what we see is that at the beginning, the error in the dimension is really smaller than the other ones. So we just iterate. So at the first iterations, the dimension is constant. And then we see that when the 2 errors get closer, then we increase progressively the dimension of the discretization space. Okay, so just to conclude, so I showed some guaranteed bounds for clusters of eigenvalues. And so the main message is that the computable bounds are usually available once you can estimate or compute dual norms of the residual. And then we have a generic framework to deal with density matrices, so orthogonal projectors in the cluster case. And then, of course, there is a balance to find between the computational cost that you can put in your computation and the accuracy of the error bound. And with that, I thank you very much for your attention.
Time for questions, and may I especially encourage the online people to ask questions as well. You are part of the workshop, so please ask your share of the questions, but also in the room here, of course. I don't want to discourage you.
Are there any plans in the works to incorporate the adaptive refinement scheme into practical codes that I one day use for like statistical theory in the way?
Yeah, I mean that kind of, yeah. We need to discuss that next week, something like that.
2 weeks.
In 2 weeks, I'm sorry. So yeah, that could be a plan to do it in like some code like DFTK, to have something that we can, I mean, we really control in a way. I would say that going to kind of even, let's say, more complicated code in the sense that they are wider used, would need that. We need some black box things, black box estimates that would be, yeah, I think a bit more difficult to get.
So is anything of what you are doing specific to plane wave discretizations and all this, or would this also work for a molecular code that uses a Gaussian basis setup?
So what I showed here is limited to plane waves or finite elements. For Gaussians, so this is what we are trying to do with Misong and Yuana. And what is difficult is that there we don't exactly know how to refine the basis. And if we add more and more Gaussian functions, then the conditioning of the basis completely blows up. And so far we haven't, like, let's say, found a way to avoid that or obtain like precise enough estimates to be able to have something really concrete.
Okay. Yeah, because normally the way we increase the basis set is basically we replace all the functions. We're not just extending a basis set that exists, but everything changes. I guess that, yeah.
Yeah, so we would like to kind of keep the part of the basis and then say, okay, we want to add a function, for example, on this nuclei, and then with this exponent. But yeah, it's not that easy, it seems.
Following up this question, I mean, already before that, you need to compute the residual in the H-1 now.
Yeah.
What are your plans for that? It sounded like this is solved.
We have kind of an idea of how to do that. No. Yeah, no, so it's not trivial, but we think that we have a way to have an estimation of that. But yeah, work in progress, I would say.
This is tricky. Can't I just do this on a real space grid also with Gaussians?
No, but basically the issue is that you don't have, well, it's tricky to get error estimates in the usual numerical analysis sense with Gaussian basis sets.
So the thing is that you need to kind of invert an operator on the continuous space. And so since you don't have that really with Gaussians, then it's complicated to invert the operator.
So the norm itself is difficult to compute. It's not that H1 is H-1. So it's a dual norm, a norm of, and that's
okay.
I mean, we could have bounds. We could have like Kruder bounds with, let's say, L2 norms. That would be a possibility. We would probably overshoot quite a bit the error, but it could still be of interest in practice.
that's, I mean, so if you have a nice mesh, which sort of, I guess you assume for Gaussians because they're working very well, then might be that's a factor, right? So it's maybe something you can just say it's a fudge factor. I mean, it's not guaranteed that, right?
It's, the thing is that it may not be a constant factor, so that you may, I think Gaspard will have a plot on that in his talk, but you asymptotically the two curves are not parallel, you overshoot more and more the error. So you have something that converges to zero, but not at the right speed. So that's, yeah.
Okay, thank you very much. The next speaker is Gaspard Kemlin, if I pronounce that right. It can be French or Russian, so. Yeah, now we have to change the.
Okay, so let's go. Yeah, so hi everyone. And first, thanks for the organizers for this nice workshop and giving me the opportunity to present my work here. So I'm a PhD student with Antoine Lévit, who was here just a few hours before, and Eric Concès, who is going to arrive today or tomorrow. And I'm going to talk about like kind of an extension in some direction of what Genevieve just presented, which is about practical error bounds for properties in plane wave, so it's very specific to plane wave, electronic structure calculation, which is a work we realized, the four of us, in the past year. So first, I'm going to spend some time to present the model we're going to use, some of the mathematical tools we need. And then I will try to spend most of the time on the results we had and how we arrived there, what is the journey we had, and why it's interesting to go in the direction of having nice error estimators for nonlinear models and also for properties that might be of interest for people doing simulation and in particular the forces. Okay, so first, to start from the start, we just look at, when we look at non-interacting electrons, what we do in electronic structure is that we have Hamiltonian, a linear Hamiltonian, the same as the one Genevieve just presented, minus Laplacian plus V. And then if we have n electrons, the total energy will be the sum of the eigenvalues. Electronic density is the sum of the squared modulus of the wave function. Okay, so this is like the basic setting. And then when we put this into a computer, we have the discretized wave function. So here we use plane waves to discretize them, and we solve a linear eigenvalue problem. We're going to use a tool that has been presented by Genevieve, which is this orthogonal projector onto the space spanned by the orbitals phi I, which is so mathematically it's a rank n orthogonal projector, n being the number of electrons. Which is nice for the mathematical analysis, but we will never store it in a computer because it's a dense, huge matrix. So we will prefer to work with the phi I directly, but we write everything with this P. And what is nice, for instance, is that the energy we had before, the sum of eigenvalue, then we can just write it as the trace of the Hamiltonian times P in the case where electrons do not interact. Okay, so what we have is that our initial eigenvalue problem is equivalent to the minimization of this trace, because I forgot to mention it, this quantity we have here, the trace, it's minimal for the P, which is a solution to the eigenvalue problem. So the eigenvalue problem is really equivalent to a minimization problem on some manifold, which is the manifold of density matrices of rank n orthogonal projectors. Okay, so this is for the nice life where electrons do not interact, but in reality they do interact, and so we have to take this into account. And using your favorite model. So it can be the Concham DFT with whatever local or semi-local functional you want, R3 Pitayevsky. All these models, we can put them into this form where we have a nonlinear term here, the ENL of P, which depends on this model. And then the problem which we are really going to work on today is this problem here, this nonlinear constraint minimization problem, from which we want to deduce if we have a solution, a variational solution, how can we compute error with respect to the ground truth quantity. So here, this parameter n, which is the size of our discretization space, if we want to have a very high accuracy, it has to be way too high. So in practice, we use smaller subspace to have like easy to obtain solution. And so here we will focus on the discretization error. So we will have a reference solution that we computed once and for all with a big N, but we don't want to do it in practice. And then we have a lot of solution for smaller discretization space, and we will try to estimate the error. And we will focus on this discretization error. So every time I will talk about asymptotic behavior, it will mean that asymptotically is when this discretization space is asymptotically big. And we will not consider all the other sources of error, such as the model error, the arithmetics error that Genevieve mentioned also. And here we will focus on how to evaluate this error for these nonlinear models for the energy, the forces, and other quantity of interest. Okay, so let's speak a bit about math before. So just I recall here the problem we look at. We need some assumption on this energy. So this is for the math people who are always happy to be sure that they can apply that theorem. So we assume that this nonlinear energy here, it's twice differentiable, and in practice, this is at least locally true. So it's not an impossible assumption. And then the second one is to assume that we have a minimizer, P star, the exact minimizer in our reference space. And we want this nonlinear energy to be quadratic around this minimizer. This is much more difficult to prove, but at least in practice, it seems to be verified. So those two assumptions are just here to be sure that we don't do crazy stuff, and they are not too expensive to ask. Okay, so to introduce what I want to speak about, I need just to remember that we work on a manifold, this density matrix manifold. So we can define its tangent space, it's a real vector space, and we will need to speak a bit about also the projection on this tangent space. Why do we need that? Is because if we take our minimization problem and we look at the first order condition, as we have to stay on the manifold, the first order condition is just to say that the gradient of the energy has to be orthogonal to the tangent space at the minimizer. Otherwise, we could still move on the manifold and reduce the energy. So the first order condition really ask this, and in particular that H and P will need to commute. And then for people that are used to work in density matrices, this means that we can go diagonalize them, and the P and H will have the same eigenvectors. Okay, we can also derive a second order condition, which is here a bit specific to the fact that we have a manifold. It's not the classical second order condition for minimization problem. It reads that if we look at the space tangent to the solution, we have some operator here that has to be definite positive. This operator, what is it? It has two terms. We split it into two. The first term is a k here, which is just the regular Hessian of the energy. So if we had an unconstrained minimization problem, if we want to find at a minimum, the Hessian of the energy is definite positive. Here we are working on a constraint minimization problem. So we have an additional operator that appears that take into account this constraint. We call it omega. Here it's its explicit definition. It's not really important, but this operator omega plus k will really be at the heart of our presentation. So it's just a classical second order condition for minimization problem, but to which we also added the fact that we had to stay on a manifold. Okay, I will just speak quickly about the numerical setting we need for the rest of the talk. So all the numerical simulation I'm going to present, they have been realized in the FTK. So it's this very nice software developed by Michael and Antoine. So it's very specific to plane wave, which is nice because the FTK is coded for plane waves. And so basically we consider here an approximation space where the Fourier mode of our solution, we bound them by some cutoff energy here. And then the space for our plane waves, our wave function, sorry, is generated here by the Fourier modes. And all the numerical simulation we will do for the first presentation here, the first result will be done for silicon, and then we will generalize them to other models. The reference space, the one in which we will compute our reference solution, we take a reference E-cut of 125 R3, and then we will consider smaller E-cuts and try to see if the error for this E-cut and the reference E-cut, we can approximate it with quantities that we can compute easily, that has to satisfy as much as possible of the conditions that Genevieve presented before. And in particular, we will look at the difference on the energy, where E is here in some smaller subspace energy, same for density, and for the forces acting on the two atoms of silicon. So we moved a bit the silicon atoms from their reference, the equilibrium position, so that the forces are not zero. And then we try to estimate the error on the forces. Okay, so the last math idea we need here is that we work with nonlinear model, and one of the track we can follow when we want to derive error for nonlinear models, it has been mentioned by Genevieve also, is to say that our residual here, we expand it around the exact solution. So here it's in a very general setting. And then at first order, we have that the residual is the residual at x star plus the Jacobian times the error. And then if we know how to inverse this Jacobian, we have an estimation of the error as the inverse of the Jacobian times the residual, which we are able to compute. And then from that, for instance, it's how we derive the Newton's algorithm. And so here we will derive bounds that are not guaranteed, because here it's only valid at first order, so we don't know if it's an upper or lower bound, but we hope that it will still give us a good approximation of the error. And so when we apply this to our model, in fact, what we can prove is that the Jacobian we need here to inverse is this omega plus k I just introduced. And this we proved it with Eric and Antoine at the beginning of my PhD. And so the formula which you really need to remember from this talk is this one, is that we will try to approximate the error as the inverse of the Jacobian times the residual. And the goal here is to say, okay, is it easy to inverse this Jacobian? If it's expensive, how can we make it easier to invert? And this is what I'm going to talk in the rest of the talk. So the first question is, how valid is this approximation? It's only valid at first order, but this first order, the higher order terms, do we need to have like very high E-cuts to have them small, or is it already valid from like small E-cut? And a way to test this, at least numerically, is to use this Newton algorithm, which I rewrote here in our particular case. And what we do is that we take a given E-cut, we find the solution for this given reference grid, and then we plug the solution in the more reference grid, the bigger one, and we just perform one Newton step in the reference grid. This we really don't want to do it in practice because it's really expensive to invert omega plus k, but we just did it as for the sake of experiment and to reassure us that this asymptotic regime in which this first order relation was valid is quickly established. And if we do this for silicon, so in blue, I plotted the evolution of the error on the energy, the density, or the forces when we just stay in our small grid. And then in orange, I plotted how this error is improved when we move to the reference grid and perform a Newton step. And we see that even for a very small E-cut here, so I take a grid, for instance, with E-cut equal 5, and then I move to the bigger grid, perform 1 Newton step, and I already increase the error by something like 4 orders of magnitude. So this really showed that this first order development is quickly established, and we can really trust it. And from this, we can already say, okay, so if this is valid, how can we estimate good error bounds? So now that we know that we can trust this relation, the first thing we would like to do to estimate the error on the density matrices is to decompose this relation using operator norm. Like if we want to know the norm of the error here, we know that it will be bounded by the operator norm of the inverse of the Jacobian times the norm of the residual. And here I'm looking, in fact, at what the L2 norm of my quantities, and this is the plot Genevieve talked about 20 minutes ago, where we see that here the quantity we want to approximate, the blue one, is overestimated by the green curve by more than several lot of order of magnitudes, and worse than that, it doesn't have the same rate of convergence. Like for small E-cut, it upper bounds the error by 2 orders of magnitude, but then when we get high E-cut, we have 3 orders of magnitude. So this is really not a good news for several reasons, a lot of orders of difference and not the same rate of convergence. So then what we can do is try to measure this error in different norms. And so if we move to, for instance, the H-1 norm of the residual, which is the residual norm here. So I have to tweak a bit my relation to make it still valid by multiplying by the good operator norms on the left and on the right. And if I plot what I get for this error bound here, I see that the green one now, which is the upper bound of the error, overestimated only by 1 order of magnitude, but we have the same rate of convergence, which is why we look at the this H-1 norm of the residual, because it has the same rate of convergence as the H1 norm of the error. Yes, and here, so it's still not good because we overestimate the error by 1 order of magnitude. But what happens is that if we only look at the error here and the residual here in a different norm, which is here the blue and the orange curve, we see that asymptotically for high E-cuts, they already they match quite rapidly. So it's not an upper bound. There is no reason here for it's not an upper bound, but asymptotically they match. So this is good news for the something we will be able to exploit in what's coming. Okay, so this was to speak about energy, density matrices, and everything. Now we can move on to forces. So in our case, in the FTK, we use pseudo potentials. And so the forces, they have 2 main contributions, local and non-local. And for the example, I will only focus on the local contribution. And in fact, if we look at the forces on one atom, like atom J in some direction, I can also write a first order expansion of the forces. Like I introduce the differential of the forces and I just write the Taylor expansion. I have that the error on the forces is bounded by the operator norm of the differential times the actual error. And if this is valid, I can then upper bound the error here with the residual and hopefully get a good bound. But what happens here is that if we had access to the true error, P minus P star, even if we had access to this, then this bound here would be really, really bad. Like we have like 6 or 7 orders of magnitude of difference here. So this is not the way to go. But remember that what we observed before is that P minus P star and the residual in H1 norm, they were asymptotically matching. So maybe that we can replace directly here the error with this preconditioned residual and hopefully not get an upper bound of the error on the forces, but at least a good approximation. And if we do that, we observe that asymptotically, the red line, which is the actual error on the forces, and the blue line, which is the linearization here, they do match very rapidly. So this is consistent with what we observed at the beginning, that the asymptotic regime is quickly established. But then, even though the error and the residual in H-1 norm, they asymptotically match, here we observe a non-negligible difference between the orange curve, where we replace here the error by the residual, and the objective curve, which is the red one. And here it's below, but it could be above in another configuration. Okay, and this is at some point we arrived here, and then we were wondering, okay, what's happening there? Because we can prove mathematically this asymptotic equivalence. So there is something going wrong here. And this is where the specificity of plane waves comes in, is that as we are working with plane waves, we're given some E-cut, we can split the reference space, the big one, between the space which have like a smaller than E-cut Fourier mode, and then it's orthogonal the space of wave function that have higher than E-cut Fourier mode. So it's kind of a low frequency, high frequency splitting. And if we do that, and we have a solution for the small E-cut space, then we know that the residual will only have components on higher Fourier modes, because the eigenvalue problem will kill all the residual in the small Fourier mode, but it will not touch all the others. And this is where the problem is, because if we look at our local contribution of the forces, then as I just said, our residual mainly have here high Fourier modes. All the small Fourier modes are cancelled. The error, we see that it's almost like the residual on the high Fourier mode here, but the actual error here, which we don't have access to in practice, but here it's just for the sake of example, it has components here that are not in the residual. And if we look at the way we evaluate the forces, the error on the forces, is that we take a scalar product against this quantity here that has mainly non-zero low Fourier modes. So in fact, the main difference between the error and the residual lies in the low frequency Fourier modes. And then we take a scalar product with something that has non-zero low Fourier modes. So this small difference is in fact amplified by this scalar product. And so the question here, the reason why here orange and blue do not match is because of this difference of Fourier modes. And so now if we are able to improve the residual only on the small Fourier mode, then hopefully we can make this orange curve to fit more with the red one. And this is what we do here. So remember the relation we have between the error here and the residual. So we decompose it between, like make a space decomposition between the low and the high Fourier modes. And we know that for high Fourier modes, it's an approximation. So we want to invert this more easily. So the lower left part of our operator here, we set it to 0 because we don't want to worry about it. And here, this high frequency part here, we know that for high frequency, omega plus k just behave as the Laplacian. And this is very nice because in plane wave, the Laplacian, it's really easy to invert. It's just a diagonal operator. So it's really, you have it for free. And so inverting omega here, which is usually expensive, in the high frequency, it will just be almost as inverting the Laplacian. And so under this approximation, the relation turns into this. And so if we invert that, in the end, we have some kind of new residual that I call Schur, because we use the Schur complement, where here we only, on the expensive grid, the high one, we don't want to do too much computation on this one, we only invert the diagonal operator. And then on the small grid, on which we already did a calculation, an SCF calculation, we invert omega plus k on this same grid, and the cost is the same as an SCF. So by doing this, you just multiply by 2 your total computational cost. And if we do that, we see that now we have a much better approximation of the error. So here, here in red, it's the actual error. And then in orange is what we get with the orange and with the first residual. Sorry. And we don't really improve the forces here. And in blue is the improvement we get with the actual error, and with the real with the sure residual I just presented, we get an improvement on the estimate of the error by 1 order of magnitude with respect to what we had with the residual in H-1. So we were able to improve the estimation on the error on the forces with this technique after analyzing where the problem was coming from. We also performed similar tests on other systems, so gallium arsenide and titanium dioxide. And the linearization is also quickly valid. It's the first numerical test we did. And we also have a significant improvement of the error. Here we want our curve to be as low as possible. And we observed we also win around 1 order of magnitude in the estimation of the error. So what are the take-home messages here? Is that when we are dealing with nonlinear problem, it's much more tricky to obtain guaranteed certified error bounds. And one way to go to error bound is to linearize our equation. And in this case of plane wave constraint DFT, we know the linearization, and it's also very rapidly valid. But once we start from there, the error estimate, which is based on the operator norm of the Jacobian, they are not good. And in our specific plane wave setting, it comes from the high frequency nature of the residual. And what we did is that we used a Schur complement to try to recover more precisely the error on the low frequency. And with this, we clearly enhanced the approximation of the forces in this way. And once then we have an approximation of this error, as we don't have an upper bound, we just approximated at first order our error, then we can either use it to have an approximation of the error or to enhance, if we know the error, then we can also add it to the actual quantity, and then we have a better approximation of the quantity. And also, if we want to, and we can pay more computational time, we can also couple again one step further, low and high frequency, to improve the quality of the estimate. The limit of this is that we don't have guaranteed bounds, so we don't check the requirements of having a bound that is always true, but it's asymptotically true. And in practice, it's useful because the expensive cost is the inversion of Jacobian on the low frequency space, and it's not more expensive than, for instance, an SCF cycle if you solve it like that. Okay, so thanks for your attention. Here you have some links that I also added in the Slack if you are interested.
Gaspard, it's interesting to see the calculations for silicon, gallium arsenide, and titanium dioxide. I feel back in the 90s again. This triggers memories, but still useful today. Questions?
But can you go one slide back on the fourth part? Is it the fourth? No, the sixth part. And when you mean the coupling between high and low frequency can be pushed further, do you mean to not neglect M21? Use slides back and do a real Schur complement.
Yes, yeah. The thing is that if you see the Schur complement I wrote here,
or not the M, yeah, but the 2-1 contribution you neglect, right?
Yes, here I neglect this 2-1 contribution, and then I improve only the residual on the low frequency. And then if I take my new residual on R1, I can not neglect this 2-1 contribution anymore and couple it with R1 here when I invert. And then you improve. So what we do first is that we improve the residual on the low frequency. And then with this new improvement, you can improve the residual on the high frequency, but it's even more expensive, and so on and so forth.
Sounds like a linear solver.
Yeah, it's in fact, if you write
it's
it,
truncated linear solver to solve this.
yes, if you write it, it's a Neumann series, and let's say I take the first term or the first or the first term.
You could also neglect the 1-2 coupling. What happens then?
The result, I mean, this one we have it for free. The application of omega plus k, we don't invert it, it does not change much.
Question also online. Okay, then we'll leave it at this. Thank you.
Yeah, that's fine. I hope that people hear me well on Zoom. So first of all, before I start, I would like to thank the organizers for giving me the opportunity to present part of my work here, and also in general for having organized a really great conference here. I really much enjoy being here. So as opposed to the previous two talks of this session, this is very much going to be from a practitioner point of view. And it might be a little bit provocative actually for practitioners, because I want to convince practitioners that the way, or the standard way they usually do to assess how good my methods are, that this standard way is actually not necessarily the best way in all circumstances. So we all know that any practical quantum chemical method always includes a range of approximations like this. The standard one is a basis set, which always has to be finite, or standard EFT implementations usually involve some form of numerical iteration. So we have some grid, the points of which also have finite spacing. And as we have just seen, to really assess the combined effects of all these approximations, this is really not trivial, right? And so in the end, we end up in a situation that is somewhat uncomfortable, because we know that we have an error, but we just don't know how large it actually is, right? But for us practitioners in a practical application, it would be actually crucial to know how large this error is, because otherwise, basically, any conclusion that we draw, we cannot be sure how solid it actually is, right? Because if we have a large uncertainty, then yeah, in principle, everything goes down the drain. And the traditional way of how people like me have assessed the reliability of a quantum chemical method is something that I call static benchmarking. Static in the sense that you have a predefined fixed set of molecules for which you have very accurate reference data, for example, from experiments or from very high level accuracy calculations. And then you compare just your method that you have against this reference data, right? And you can come up with some error measure like the RMSD or mean absolute deviation or whatever you like, right? And as I would like to show in this talk is that exactly this approach has some shortcomings that are not so trivial to resolve. And we have recently published a paper, it's on arXiv, and it's also accepted in PCCP just like about an hour ago. I actually received the email with the definite page number, so that footnote is already outdated by now, but never mind. So the starting point of all of that is the fact that the errors of quantum chemical method, no matter what method, but the errors of quantum chemical method are always distributed heteroscedastically across chemical space. So that means they are not distributed evenly. So for a given quantum chemical method, maybe that delivers really good results for a certain class of compound, but it can actually really fail utterly for other compounds. Or you can get really decent results for a certain property, but if you're interested in another quantity, the same method might actually let you down. And so for that very reason, everybody has for a long time now accepted the fact that if you really have a small benchmark, such as a handful of molecules, like 5 molecules or so, this is never going to be representative for the actual case that you're dealing with, right? You cannot just transfer these results to a completely different class of compounds. And then the way people tried to address that was that they just continuously enlarge these benchmark sets. And by now, actually, so over the past decades, people have really worked on that. And by now, we actually ended up with really huge benchmark sets. But one example is this one that Marty Rossian and Ed Gordon published in 2017. It has about 5,000 data points, right? And it includes a really broad set of properties like atomization energies and reaction barrier heights and so on and so forth. One point that I would like to mention here is that my conclusions, I think, are valid for any benchmark set. I use that one specifically for my work, simply because of the fact that this data is really available in an easy way and in a way in which it is also straightforward and easy to work with. But in principle, you could take any other benchmark set and you would arrive at, in principle, the same conclusions. And so the key idea that we have, or that we wanted to do, was to subject this benchmark set to a statistical analysis to then understand how conclusions with respect to accuracy and transferability of the result depend on the composition of that benchmark set. So one, in principle, easy question to start with is you can ask, well, what is actually the influence of a single data point? And naively, you could expect that if I have like a large set of 5,000 data points, just removing a single data point, it cannot be that large of an influence, right? And a trivial way to understand what this effect actually is by checkmapping, right? So you take a full data set of 5,000 points and you create a new data set that just lacks the first point, right? And then you create a second new data set that lacks the second point. And you create a third data set that lacks exactly the third point and only the third point, and so on and so forth. And then you do the entire benchmark all over again for that second set, for the third set, and so on and so forth. And this is what I did, and this is what you see here. So here you basically see the RMSD of PVE for every of these check-knife benchmark sets, and I just made a histogram. Why for PVE? I just happen to like this density. I also did it for all the other density functions in that set, and sure, the numbers change, but the qualitative picture always remains the same. Okay. And so when you look at this histogram, so please note that this is a log plot on the ordinate axis. So basically everything is playing up here at between 7 and 7.1 kcal per mole. This is also exactly where basically the reference RMSD of PVE, so the RMSD of PVE that you get with your original benchmark set, where it lies, right? And so you would actually think that for all these sets, and these are really like almost all the sets, removing a single data point doesn't change anything. And this is certainly very common, right? But then there is also this thing, and this is marked in this red box here. There are a few data, but really only a few, but still they are there. And when you leave those away, the RMSD changes unexpectedly much. Sure, I mean, the absolute error, the absolute difference here is like 0.2 kcal per mole. It's like nothing a chemist would ever worry about. And also the relative difference there is like 3%. But still, you leave away one data point from 5,000 and the result changes by 3%. That's like not so nice, right? And then you can build upon this idea. You can actually say, well, now I'm doing a very nasty thing. I'm not only leaving away one data point, but I'm leaving away maybe 10 data points. That's still not so much compared to 5,000. And like on purpose, I leave away the 10 data points with the largest error. And then you do, with 4,990 data points, again assess the RMSD of PVE, and you notify that now actually it has dropped by a striking 17%, which is like, wow, right? And that's not even like the most like extreme case. If you take like omega B97RE, which is just a different density functional, removing the 10 data points with the largest error makes that density function appear 31% better, right? And so like the first conclusion or a first take-home message that we can take away from that is that even if you have a really large benchmark set, removing only a few data points, really only a few, like 1% or so, can already drastically change your conclusions that you have with respect of the accuracy of that method. Now you can ask, well, why is that, right? So why are there a few data points that have such a large influence? So let's have a look at the data points, and that's exactly a histogram of the data points. So the errors that the PVE has. Again, that's a log plot, so almost everything is happening here between 0 and 20 kcal. But then, and this is marked in red here, there are a few data points that have much, much larger errors, like reaching up to 120 kcal per mole. And it's exactly these data points, of course, that if you leave these away, these are the ones that really drastically lower the RMSD, right? It is somehow logical. And then you might ask, well, but why is that? Right? Is that, I mean, to me, this distribution doesn't really look sane in a way, right? It looks somehow strange and skewed. And you might ask, well, is there something wrong with like these data points that have such a large error? And then you investigate these data points and you see that actually these are basically absolute atomization. That's an extensive quantity, it just grows with system size. So if you have a larger molecule, of course, the atomization energy is also going to be larger. And then just assuming that my relative error is always constant, then of course, for a larger molecule, my absolute error is always just like increasing. And this is exactly what is happening. So if you look at that point at about 120 kcal per mole, the relative error is just like 0.04%. That's really not a lot, right? Because like down there, where you have different properties like reaction energies and so on, you sometimes have relative errors that are much, much larger than that, 1% or even more, right? But the absolute value is just much smaller. So there is nothing wrong with like these data points. It's just how it is, right? And so this picture basically really illustrates the first starting point that I said, that the errors are not distributed evenly across chemical space. There's nothing you can do against that. And that really breaks down your approach of using this to assess the accuracy of your method. Because if you're now basically mangling all these kind of errors together in just one average data measure or error measure, then of course this error measure is going to be too large for certain parts of your chemical space and too small for others, obviously, right? And so for a practitioner, this is of course bad, because if I'm really just interested in a certain class of compounds or a certain application, I don't really care. So maybe, I mean, let me go back one slide. Maybe I'm absolutely not interested in atomization energies for my particular application, and I basically don't matter or don't care about these data points, right? And then these are basically just skewing my error, because they artificially increase the error that I truly have in the case, right? So I really advocate that what people should do here is to adopt a system-focused approach. Application. All right, so at that point, I would like to stand a little bit back and showcase like other parts of our work and show how this basically ties into that overall vision of having like system-focused benchmark and what you actually could also do with that. So one thing that immediately like jumps to your mind is that when you have such a very nice system-focused benchmark set for your particular application, you can of course use it to estimate the error of your method. But why not also using it to improve the method that you have? So for example, when you're doing DFT calculation, you have a very nice set of reference data. Why then not use that to basically create or reparameterize a density function such that it is as good as possible for your particular application? And as we have seen in other talks today, and already actually yesterday in James Ramoda's talk, you can do that, especially for density functions, including uncertainty estimation, such that you basically do not just parameterize one density function with one set of parameters, but you essentially have a distribution of parameters leading to an ensemble of density functions, and then you can have an ensemble of values that you get, right? And you can use that as an uncertainty quantification. One conceptually simple way of getting such an ensemble of parameters is not the one that we actually used here in reference 4. In many different cases, a conceptually simple way of getting like an ensemble of parameters is bootstrapping. So when you have your data set, and then you create or you synthesize new data sets by sampling from the original data set with replacement, right? And because you do that with replacement, the new data set that you have is slightly different from the original one, because, for example, it might contain the first data point of the original set twice, or even 3 times, or something like that. And then you do that several times. Typically, you end up with something like 10,000 of these bootstrap samples. So now we have like 10,000 slightly different benchmark sets, or slightly different reference data sets. And then we just take our model that we have and parameterize that on each of these 10,000 sets, yielding us, in essence, then 10,000 slightly different models, and then we can use these 10,000 models, this ensemble of models, to arrive at an uncertainty quantification. And the first, somehow, simple model that we used was exactly what also Christoph Jakob was mentioning yesterday. This was what you asked, this model of the isomer shift as a linear function of the contact density. This is something that Johnny Poppe did back in 2017. And then bootstrapping is a simple thing to do, and it doesn't, it is in no way specific to the linearity of the thing that we did in reference 5. So it's easy to generalize to other models, and this is exactly what we then did. And in particular, we use bootstrapping to come up with a simple and straightforward method and also program to quantify the uncertainties of semi-classical dispersion corrections, in particular these dispersion corrections, which are like everywhere nowadays. And it's good to know their uncertainties. All right. So one thing that I basically swept under the carpet, like the slide before, is that how do you actually manage to come up with such a system-focused reference benchmarks, right? Because say I have just a set of molecules in which I'm interested in and pretend that I actually have accurate reference data for every single molecule, then why should I actually bother with the low-level results, right? I can just take the high-level results that I have for all the molecules and just use them, right? And the obvious thing is, of course, that doing such high-level calculations for all your molecules will probably not be possible just for time reasons. And what we propose to do is that you start with a set that is as large as possible, but still manageable, such that you get for like 1/10 or so of your molecules, you get accurate reference data, such that you know the accurate error at that point, and then you use a machine learning model, be particularly fancy Gaussian processes, to learn the error, right? And then you use that to predict the error on all the other molecules that you have. Okay? And as you're basically expanding that and predicting the error for other molecules, at a certain point, this machine learning model will basically become too inaccurate because it does like too much extrapolation. And at that point, especially Gaussian processes are really suited because they have a built-in measure of the uncertainty. So we basically cannot only use that model to predict the uncertainty, but it also gives us the uncertainty of the uncertainty. And if at some point this is then too large, we know that we can no longer trust our machine learning model, and we have to bite the bullet at that point, and we have to regenerate or to create additional reference data with our high-level method. And with that, we can then retrain our Gaussian process and basically start all over again. And this is something that we have showcased as a proof of concept here in reference cell back in 2018. And we have also extended that, in particular to the 3 dispersion corrections. This is reference 9, which I would like to really showcase, especially because this is exactly the poster that is presented by Stefan Bugler at this conference. It's still hanging upstairs, so if you don't yet know it, be sure to drop by. And one last point I would like to mention is that, or maybe I have to take one step back. So why are we actually interested in doing all this uncertainty quantification for like rather low-level methods? That's because in our group, we deal a lot with the exploration of very complex chemical reaction networks. Complex in the sense that you easily end up with millions of calculations that you have to do, right? So you just cannot afford to do couple cluster for all these methods, these molecules, right? And then when you end up with like a million calculations and really like thousands of compounds and reactions between them, not only is the computational overhead starting to kill you at some point, but also when you just want to understand the results, just want to visualize this reaction network, what you get is just like a very complicated graph with a lot of nodes and many, many edges in between, and you don't understand anything, right? And a very elegant, because physically motivated way of like pruning this mess is to subject it to a kinetic model, right? So in this simplest case, you could just, for all the reactions, basically estimate the barrier. And if the barrier is above a certain threshold, you just neglect it because you say that barrier is not going to be climbed over at, my temperature. And you can take that even one step further and do a proper kinetic analysis, and then just neglect all the species, the concentration of which is below a certain threshold. And you just say, well, this species essentially never shows up, so I just neglect it. And that, of course, dramatically prunes the number of calculations that you have to do. But at the same time, it really cleans up your reaction network, right? Because all of a sudden, many nodes and connections between them just vanish. But this very example, and this is why I put it here, really showcases why uncertainty quantification is so extremely important for us. Because even if I have an energy, like an activation energy, which has like a decent accuracy, right, ±1 kilojoule per mole, that's something you can really be happy with, right? If you then use that energy to create a kinetic rate constant, right? For example, with the Irene equation or a more involved model, you always have to exponentiate this energy, which also means that you exponentiate the error. And even with a considerably, or something that is considered a very accurate energy, all of a sudden your rate constant can be orders of magnitude off. And so you just need to be able to know that, right? Because otherwise you can just be completely lost and do something that has nothing to do whatsoever anymore with reality. All right, with that, I would like to come to the conclusion and sum up. So really, I think that the fundamental issue that really practitioners face with like the traditional static benchmarking is the fact that the errors are distributed not evenly across chemical space. And that means that the results that you get in some benchmark set are not directly transferable to your practical case. And if you assemble from a broad benchmark set that basically samples all the chemical space, even if that would be possible, right? If you then use that to basically justify or quantify the uncertainty of your method, that is still not good for your practical case, because this average measure actually underestimates the error for certain cases, but it overestimates them for other cases. And like a straightforward way to overcome that is to adopt like a system-focused and rolling benchmark, where you quantify the error on a small set of molecules, train a machine learning model to be able to propagate this error to all the other parts or the other molecules that you're interested in. And as soon as that machine learning model lets you down, you in a rolling fashion create new benchmark sets to retrain the model and then be able to continue from there. All right, with that, I would like to thank my boss, Markus Heyer, and all my group members. Financial support by ETH Zurich and the Swiss National Science Foundation is gratefully acknowledged. And last but not least, I would like to thank you, ladies and gentlemen, for your kind attention.
Thomas, I'm a bit puzzled by your first example of this atomization energies.
Yeah.
I would say some quantities are more naturally expressed by relative errors and some by absolute errors. So if the relative error is what matters, why bother about that?
Yeah, true. I mean, you can of course do both, right? Here we basically stuck with the absolute error, because this is also what Marty Rossen and Gordon did in their analysis. So we try to basically follow that as close as possible to show how such analysis, can be flowed, in particular here because it's the absolute error that is problematic. But I mean, in some cases, you're not. Yeah, sometimes you're interested in the relative error, and then you're fine. But sometimes you're also interested in the absolute error, and at that point, it gets critical, especially for size-extensive.
Yeah. Okay. It depends on.
It depends really on the actual use case, right? And this is another thing that is traditionally not represented in such benchmarks.
Yeah.
Pascal has a question.
Great.
Yes, thanks, Thomas, for your very nice presentation. You mentioned in your last slide that an important point is that errors are heteroscedastic, and so that's I think a good point to use validation techniques as I presented on Monday, or as Michele presented. What kind of validation methods do you use for your applications?
For what we use for our predictions, yeah, it's a good question, because we actually started to look into exactly like the calibration and sharpness framework that you proposed recently, but we didn't make actually too much progress there. It's just like, time and other resources are just finite, and so you just cannot advance on basically all the fronts as fast as you want. But yeah, we're very much actually basically looking at exactly your work in that area.
Okay, thanks.
Yeah, Thomas, we had part of this discussion before, but on the way that you're describing these benchmark sets, I think it's not completely fair to just boil it down to one number. I think this is not what the people developing these sets are really intending, because if you these are split up into lots of subsets, and in the end, if you're looking at want to look at atomization energies, you can look at the atomization energy subset or very high subset or whatever. And there are these huge tables that you can.
That is your slide, right? This is exactly your slide. So this is basically this large benchmark set of 5,000 points. This happens to be subdivided into 84 subsets, right? And one of these subsets is, I think, is like the third. Yeah, it's here. It's called AE18. That stands for atomization energy, and the 18 refers to the fact that there are 18 data points. So yeah, it is actually true. These large benchmark sets are usually subdivided into, like, different classes of compounds, or according to the properties, or both. Sure, and like people are constantly raising this transferability issues, right? I mean, I'm by far not the first one raising this here and now, right? This has been raised, like, I don't know, like 20 years ago, basically for all the time I can remember. But there are like 2 points I would like to reply to that. So the first point is, like, so especially in that paper where they used exactly that benchmark set, they said it's very important not to basically convolute everything. And so they basically just, instead of giving one table where they rank everything according to, like, the overall error measure, they give 85 tables. In like the first 84 tables, they just rank it according to every single weight subset. And then at the end, they still go back to that overall error measure. Because for some reason, computational chemists are always really much going to really just rank everything by one single number. For some reason, we just have to do that. I don't know why, right? So that's the first point. And the second point is, like, okay, so I'm only interested in optimization. So I throw away everything here except for this AE18. But then it might still be that these 18 data points have absolutely nothing to do with the particular molecules I'm interested in. And is it then really still reliable or not so much? It's difficult to say. It's probably more reliable than if you take everything else in addition, but not necessarily extremely.
But I mean, the other way around, and that's kind of what you're advertising for. For my specific problem, I can pick the subset of this benchmark that is most relevant, which is still not as focused as what you're advertising, but it's going in this direction.
Yeah, sure. I mean, if any of these subsets, or even a multitude of these subsets, basically suits to what you're actually after, sure, that's a perfect starting point. But just like from the multitude of possible things you can be interested in chemistry, I just boldly claim that 84 subsets isn't really not even covering half of it, right? Yeah. So sometimes you have to start from scratch. Sometimes you can use such things, of course, right? I'm not saying you should never use anything of that. By far not, right? That's not my intention. That might be a really good start. And in special circumstances, it might even be everything that you actually have to do. Sure.
There is a question online.
Yes.
Yeah. Hi, Thomas. It's good to see what's happening in Zurich. What I want to know is you use the term system specific, and I'm a bit curious here what exactly you mean by this. Is it something that the user defines? Is it something that you can objectify? Are there objective criteria that you can apply to determine what system specific means? Because I think this is quite an important detail.
Yeah, no, system specific with that, I really mean something that I as the user specify. So I have a certain application I'm interested in, I don't know, like homogeneous hydrogen transfer with ruthenium catalyst or something, and then this specific molecules. These are the systems I'm interested in.
Okay. Because I was just thinking about cases where maybe my chemical intuition may mislead me, where I would overlook similarities that are there, but I don't recognize them.
It's a very good point, yeah. This is really a very interesting point. Yeah. Thanks.
Okay.
So if I got that correctly, when you do that, you build your benchmark test. Then for a part of that benchmark test, you calculate with a very accurate method, and then with your method, take that error and then train that with a machine learning model for the rest of the. Okay,
exactly.
So roughly what percentage of that set do you need to train with the exact method to actually trust a machine learning model enough to validate DFT?
That really depends on the diversity of your set, right? So if your set is really greatly diverse, if like the overlap between the individual data points is such that basically no data point has anything to do with any other, then it's almost, right, I mean, just conceptually speaking, then it's like almost impossible for a machine learning model to really trustworthy extrapolate. And then you basically have to just expand your set for which you have to calculate the high level method, basically everything, right? If all the molecules are really, really similar, then maybe 1% or so of the data is already enough. The point is that like the way we approach that is really in this focus, in this rolling way, in that we just start with really as little data points as possible and then train on that and then just look, if I just apply this first generation of machine learning model on the next round of points, does it give me something that is below the uncertainty that I can live with or not? And if not, I just include them and retrain. And if it's actually good enough, then I go as far as I can until eventually my machine learning model is no longer trustworthy for me. And at that point, I start to retrain.
Thanks. Okay, I see no further questions. Then we can thank Thomas and unless the organizers have some announcements for tomorrow or
small announcement. We meet tomorrow at 10. So tomorrow is still at 10. And with the official discussion session.
okay, that was an important announcement.
Auch schnell das jetzt abschalten.